Hello, everyone. Good morning, good afternoon, good evening, depending where you are. And welcome to this Ophir Photonics webinar. My name is Mark Slutsky. I'm the product manager for power and energy measurement solutions here at Ophir Photonics. And thanks for joining us today. Hope everyone's staying healthy and, well, all that stuff. Okay, the topic that we're going to be talking about is, in a sense, I suppose we could call it a niche topic, but not a small niche. We're going to talk about issues, concerns, best practices, things to look out for related to measuring beam power, laser beam, but not only laser beam, as we'll see, using photodiode sensors. Generally, we'll do that when we're talking about relatively low powers, but I don't want to steal my own thunder. Just before we begin, some logistical notes. The total time of this webinar should be approximately 52 maybe minutes, something like that. Questions, comments are welcome and even encouraged using the text chat box on the right side of your screen. And I'll do my best to answer either in real time or at a suitable point in the flow of the information, depending on the nature and the timing. If I'm already mentioning that, then I'll mention also that I'll be leaving my contact information up on the final slide for a couple of minutes after we're done in case anybody wants to contact me offline. You're welcome to do that as well. And if I'm already mentioning that, then I should also kind of mention the obvious that you can get a hold of me, us, someone, either through our website, www.ophiropt.com, or going through the MKS website, through either the Ophir office or our representatives in your various countries. If you don't know who they are, then on our website, on the top main menu, I believe it's the right-hand side of the menu, there's a Contact Us page, and there per country you can find out who to speak to. And on the bottom of, I believe, every page of our website, there's a Contact Us form of some sort. I don't remember if I think that's what we call it. So we do want to make it as easy as possible for you to get a hold of us if there's any way at all in which we can serve you, or if you want to speak to us about anything. I'll probably repeat that little bit somewhere towards the end of the webinar for the benefit of people joining in late. Okay, so let's begin then. We're not going to be going into any great engineering depth. Our goal here isn't to turn anybody into a photonic measurement instrument, laser power meter design engineer. It's a cool thing to be, but that's whatever. Our goal here is to basically share as much maximally useful information as possible with as many of you as possible. And not, and the goal, another thing that it's not is, the goal is not to serve as an ad or a plug for Ophir products and solutions, even though they happen to be good. So with that in mind, I've put in a lot of effort to try to keep the information as generic as possible. As you'll appreciate, when it comes to using specific examples of actual instruments, there I'll be referring to Ophir instruments and Ophir solutions, because obviously those are the ones that I'm able to speak about. Okay, so with all of that introduction out of the way, we can move forward. I'm assuming you're at least somewhat familiar with Ophir, whether you're already using Ophir solutions or you're evaluating, or whatever the case is. You may or may not know, some years back we were acquired by Newport, and then some years after that, Newport, along with Ophir, became part of MKS Instruments. Basically what it says on this slide, if I may drastically boil it down to its essence, we like to do the hard stuff that you would be happy to get off your head, so you can focus on your work where you bring your added value and not have to lose any sleep over the tools that you need to help you get your work done. I think that's a pretty fair, précis, fair summary. Okay, so here's what we're going to be covering. Again, we're not trying to turn anybody into a measurement instrument design engineer. I just want to give a quick overview of the real ABC basics of photodiode sensors, just so that we're on the same page, speaking the same language. And then we'll start getting into specific issues and where the challenges that they present. And as you'll, I hope, see very quickly, even though I said it's a niche and then maybe not such a narrow niche, but it turns out that it's very often not nearly as simple as it may sound. And I think that's probably true for any kind of engineering or technological discipline. So these are the items that I chose to cover. These are items that just come up all the time with our customers. So we're going to talk about measuring. We're talking about measuring power, or what we call average power, as opposed to peak power or instantaneous power during a pulse. But I don't want to get ahead of myself. We're going to look at that because that's an important one. So first, we're going to talk about some of the issues, concerns involved in measuring the power of pulsed beams and solutions that deal with those. We're going to talk about angle dependence of photodiode-based sensors. And related to that, we're going to talk about measuring power in applications involving widely diverging beams. Then we'll talk about saturation, specifically how do you know when you're in saturation? Not always as obvious as you might think. We'll talk about some ideas related to beam size. How big, how small should you make your beam to measure it most correctly? And then we'll talk about some issues related to spectrum, the spectral distribution of the sensor in light of the spectral distribution of the beam that we're trying to measure. Okay, so with all of that, we'll begin. And I hope that by the end of our discussion, if not sooner, you'll have some appreciation, you probably do already, of I'm not sure how to word this, but of our uneasiness when we get the question, which we get all the time, I only need to measure a couple tens of milliwatts or something like that. I realize I'm going to use a photodiode. Why do I need to buy a calibrated laser power meter? I can just, buy a photodiode off a, catalog website for I don't know how much, and I can put together, or I have engineers who can easily put together an amplifier. Like, why do I need this? I hope, if it isn't already clear, the answer to that will become very clear long before we're done our conversation today. All right, so let's begin with the overview. Talking about semiconductor photodiodes. We're not going to get into the physics of semiconductors, but you basically have a PN junction. That's about as physics as I'm going to get. It's a device. Photons of light come in. Okay, I was just being a physicist again. Photons of light come in, creates a separation of charges. The electronics that are connected around this device turn that separation of charges into an electrical current, and the current is proportional to the power of the beam that came in. The constant of proportion is what we measure when we calibrate this thing. And that way you can eventually get a measurement. So light comes in, electrical current goes out, we get a measurement. These kind of detectors are generally physically, their response time is very fast. The response time is on the order of nanoseconds up to microseconds, depending on A, B, C, D, and E. They're also quite sensitive. They can be used to measure optical powers, nanowatts, sometimes picowatts. Now, I'm going to focus a little bit on this fast response time, and you'll see why momentarily. So here we have a pulsed laser. Okay, for higher powers, like typically tens or hundreds of milliwatts and upwards to 100 kilowatts plus, we usually use a thermal detector, a sensor based on a thermal detector, thermopile usually, to measure the power for all kinds of different reasons. Those kind of sensors have a physical response time on the order of a second or seconds. So if we are using such a detector to measure a laser that's pulsing at a couple of hertz, the sensor has absolutely no clue that the power that's coming in consists of repetitive pulses. It thinks power is power. At best, or worst, depending on how you look at it, if it's pulsing slowly enough compared to the time constant of the particular sensor, there might be a little bit of a ripple in its output signal, but not more than that. So you can't use thermal sensors, not standard ones at least, to measure the energy per pulse of a repetitively pulsed beam. We use other detectors for that, pyroelectric or semiconductor again. A photodiode, a semiconductor, on the other hand, because the physical response time is fast, if the laser is pulsing, obviously if it's pulsing at gigahertz, it's not going to be so simple. But if it's pulsing at hertz, kilohertz, tens of kilohertz, the photodiode has absolutely no difficulty having its output signal, that electrical current, keeping up with the laser pulses. All right, that's going to become important in a sec. Okay, I apologize for this. This often happens when I go from PowerPoint to WebEx, and I think it's because the PowerPoint that I'm using, the Microsoft Office, is Hebrew enabled because I'm in Israel, and somehow or other the left-right directions get a little bit wonky in the move from PowerPoint to WebEx. Sorry about this, but you already know what it says here. So basically, photodiodes are highly sensitive and generally saturate at powers on the order of a couple hundred microwatts that are a little bit low for the needs of many applications, particularly laser measurement applications. So the dynamic range for the sort of applications that we usually are looking at, we're going to want to both broaden and shift the dynamic range. Oh, I skipped over one small point. I'll just mention that briefly. We configure these photodiodes, even though they certainly are fast enough to measure energy per pulse. And as I mentioned, we do often employ photodiodes in energy per pulse sensors. But usually we're talking about power measurement. We, at least at Ophir, but I think everybody in the industry does this, we configure the sensor for measuring average power. So we slow down the response in the meter, in the output, the display, the other end, the user-facing end of the measurement instrument, because it's going to be doing some calculating and signal processing and converting the analog reading into a numeric digital output or a digital direct interface with some software, whatever it is. But because we're measuring average power, that's not normally a problem at all. So in Ophir meters, when we're using a photodiode-based power sensor, the response time with the meter at the end of the day, from the time the laser beam turns on until the user sees the number 2.3 milliwatts, let's say, displayed on the display screen of the handheld meter, 0.2 seconds. Okay, we're going to revisit that also in a couple of minutes. So back to the dynamic range. So what we do in order to make the dynamic range of these things a little bit more useful for the kind of applications that we're looking at, photodiode sensors generally that are meant for laser measurement applications, typically they have an attenuating filter integrated onto the photodiode to enable them to measure higher powers than they otherwise would, and giving them a more useful dynamic range. And at Ophir, we also add a second removable filter in addition to that first built-in attenuating filter, so that by removing and then replacing that second filter, we're effectively extending the dynamic range even further. So here's schematically what it looks like: the photodiode, the built-in, if you will, attenuating filter, and then that second removable filter. Our service teams over the years would very often have sensors sent in for repair because somebody kind of pushed their finger through the attenuating filter, that removable filter, while trying to take it off or put it back on. So we actually have a series of photos on our website that show how to take it off and click it back into place without, sticking your finger through it. Wait, there was something else I wanted to say here. Right. So typical power ranges for Ophir photodiode sensors, and again, this is reasonably typical, I think, is from nanowatts. Actually, we've got some models that can go down to a few tens of picowatts, up to usually a couple of hundred milliwatts. Some models go as low as, I think, 20 picowatts is the most sensitive that we have in our photodiode power sensor range. And some models go as high as 3 watts by means of a special design of that second removable attenuating filter. I'll say more about what that special design is soon. Okay. Another trick that we add to some of our photodiode sensor models, at Ophir at least, to help with when we're working at those lowest powers, is background subtraction. If you're measuring, in some scientific application, you're measuring, I don't know, a couple of nanowatts in a darkened lab, and a little bit of light is seeping in through the crack under the door, that little bit of light could very conceivably be significant relative to the nanowatts that you're trying to measure. So what we do is we have, I don't know if you can see that here, we have 2 photodiode detector elements connected one next to the other. the concept is that the laser beam that you want to measure is going to be incident only on one of them. The background light, it's a pretty safe assumption that it's reaching both of them equally. And the instrument automatically subtracts one from the other, and that gives actually something like a 98% effective background subtraction. So that's a neat trick that we use in some of our models. Okay, that was the overview. No, sorry, that was the overview. So measuring oh, I don't know, that was weird. Okay, sorry about that. I had an extra copy of my agenda slide in there because we were talking about okay, never mind. Senior moment. Okay, so measuring pulsed beams. The real interesting market segment involving pulsed beams is those applications that make use of VCSELs. They have very strict measurement needs and very significant challenges. So for those of you who don't know what I just said, VCSEL stands for vertical cavity surface emitting lasers. These are a type of semiconductor laser diode. Unlike the more typical or the more standard, more classic maybe, edge emitting laser diodes, VCSELs emit upwards. And so they can be easily packaged as an emitter array containing hundreds of emitters on a single chip. They can generate powers from milliwatts all the way up to a couple of watts. Some unique properties. Because they're tightly packed, they would need to operate at very low duty cycles, meaning short pulses and relatively low frequencies because of thermal issues. Otherwise, they're going to overheat. For some applications, this is perfect. For example, very typical application of VCSELs would be things like high peak power short pulses are just right for any kind of distance measurement, LiDAR. So VCSELs are becoming the light source of choice in applications such as face and gesture recognition, which involve LiDAR, where unlike a camera-based face recognition system like the one used in my cell phone, which in theory could be fooled by a photo or might not recognize me if I don't know, my face is a little bit different. These project an array, this is really cool, project an array of something like 30,000 laser dots onto the user's face, and the distance to each dot is measured in the sense of a LiDAR distance measurement, and that creates a map of the person's face, and that can't be fooled by a photo. These are used in proximity sensors, augmented reality displays, also higher power applications like LiDARs for autonomous vehicles or robotics and UAVs and things like that. So these are small devices, typically battery powered, so power issues can be critical in the success of an application or not. Combine that with a need to, let's say, project 30,000 laser beams onto a human's face, and it's kind of easy to appreciate the importance of measuring the relevant parameters and very tightly controlling them. Power, very often also pulse shape, which is going to determine the resolution of distance measurement, and sometimes spectrum. Now, VCSELs, so as we said, typically are operated with short pulses at low rep rates, high peak powers, meaning high instantaneous power during the pulse, and then a relatively longer time of zero power before the next pulse. And generally speaking, the beams are widely diverging as well. We're going to come to diverging beams soon if you remember the agenda. So let's talk a little bit about issues related to the repetition rate of these pulses. Photodiodes are typically fast response, as we said, nanoseconds to microseconds, which means, as we saw, if you remember that graph, the output signal of the detector has no problem keeping up with the pulsing of the beam, as opposed to slower sensors. Typically what happens is in a laser power meter, you've got the sensor, whether it's photodiode or something else, and it sends out a raw analog electrical current, as we said, that's proportional to the power being measured. And then you've got the meter, the display, the console. Every manufacturer uses a different word. You get the idea. Might be a handheld meter, desktop, whatever. And the first thing that analog current meets when it comes up to the meter is the front end, the A to D sampling at the entrance point into the meter, the analog part of the meter. Because we're talking about power measurement, the sampling rate for the input A to D is typically, well, at Ophir we use 15 hertz. Another manufacturer I know uses 20. That's the order of magnitude. So let's consider two possibilities. First possibility is where the pulse rate is not an exact whole number multiple of that sampling rate of the input. Maybe let's say 10 hertz pulse repetition rate, and we're sampling that signal at 15 hertz. We're going to get a beat frequency because of the meeting between these two frequencies. In this case, 15 hertz sampling of a 10 hertz signal. And remember, the signal coming out of the photodiode is also going to be going up and down at 10 hertz because the photodiode has no problem keeping up with the pulse rate. So on a display using a moving line graph, just so you can see the problem, we're going to get the measurement output jumping up and down at the beat frequency, which is going to be the difference between 15 hertz and 10 hertz. So here we've got the thing oscillating at 5 hertz. As you can see, not very easy to get a measurement out of this thing. So that's one problem if the pulse rate is not a whole number multiple of the sampling rate. So problem number one is going to be a beat frequency. Problem number two is if the pulse rate is, yes, an exact whole number multiple of the sampling rate, let's say 15 hertz. So let's say it's the pulses are coming in at a rate of 15 hertz, and I'm sampling them at 15 hertz. Now here it depends on how the A to D of my instrument is designed. More so in older designs than newer designs, but still, in many types of A to Ds, the laser pulses are coming in at 15 hertz, meaning there's 660 milliseconds, or sorry, that's a mistake, 66 milliseconds between each laser pulse and 15 hertz. And once each cycle, my A to D opens up, takes a sample, and then closes. In more modern instruments, it stays open through the whole window, so this problem won't actually come up. But I know at Ophir, some of our older instruments used to have this problem, and that's why I felt it's interesting enough to share it with you. So as you can see now, what happens when the sensor, a light pulse comes into the sensor, the analog signal maximizes and then slowly drops back down to zero. It's not a Dirac delta function, if you remember that. The drop takes time. So if my sampling takes place early in the cycle, I'm going to get a high reading. If my sampling takes place later in the cycle, I'm going to get a lower reading. So the power reading that I'm going to get is going to be dependent on the phase of my A to D sampling. That's no good. Okay, so that's another potential problem. As I said, more modern instruments usually use a more sophisticated kind of A to D, but some older instruments, and older, I don't mean 2,000 years ago. I mean some instruments that, not that many years ago have this limitation. Okay, here we see what a low average power but high peak power or high instantaneous power signal might look like. Okay, let's think about this for a sec. What power scale do we set the meter to? If we choose, okay, again, we've got high instantaneous power, high peak power, and then 0. The average power, which is what I'm trying to measure here, is going to be this red line over here. Now, if we choose a power scale or range that's appropriate for the average power, as we normally do when we're measuring power of CW beams, then we're looking at a low average power scale, meaning high gain in the electronics. But then when the pulses come, the detector is going to saturate, or it may very likely saturate, which can lead to a measurement error. And even worse, because the average power is within the range of the scale, then my instrument might not even realize that we're over range, and so the user won't be given any kind of a warning that something's the matter. But because during the course of the pulse, the meter was, or the sensor, the meter, both, were momentarily saturated, the reading could very possibly be wrong. If, on the other hand, we want to avoid saturation, and so we select a scale appropriate for the high peak power, meaning low gain in the electronics, then we want to set the scale so that this doesn't saturate the detector. Then we'll be operating the parameter we're trying to measure, the average power, is going to be near the floor of the scale, and we're going to suffer from poor resolution and lots of noise. In other words, any scale we choose will be wrong. And this is quite typically how VCSEL output signals look. So at Ophir, at least, we have a very interesting solution that we came out with a couple of years ago, supported by many, not all, many of our meters, and we call it the low frequency power mode. It takes care of both of these problems. The sampling rate is adjusted to match the actual pulse frequency, which the user is prompted to enter. So it's not fully automatic. It's maybe what we can call semi-automatic. So no more beat frequency. The gain and the A to D, we're talking about more modern instruments, so we anyways are not going to have that phase-dependent reading issue. The gain is lowered and the resolution is increased automatically so that we get accurate measurements of the low average power without being thrown off by saturation caused by the high peak power. So it's a very elegant, clean solution, and here you can see the line is clean, even though we're still pulsing our laser at 10 hertz and our sampling rate would have been 15 hertz, but it isn't because we're using low frequency power here. All right, that's cool. Just as a by the way thing, many instruments, in addition to the normal 15 hertz or 20 hertz or whatever it is, input sampling rate when they're measuring average power from a power sensor, also have, I don't know if many have, I know at Ophir we have one instrument that has a fast power mode where you can set it to sample the power signal, but at a high sampling rate, not a low sampling rate, at 10 kilohertz in our case, so that you can keep up with the pulse shape, and that gives you all sorts of additional analysis capabilities. Just if we're already talking about pulse energy, you remember this, the slow sensors and photodiode sensors. Because photodiode sensors can keep up with fast pulse signals and therefore could be momentarily pushed into saturation, we, in our specifications for photodiode-based power sensors, in the Ophir data sheets, we also give the maximum pulse energy, even though the sensor is not designed to measure pulse energy, but it could be affected by pulse energy. So this way the user knows, I have a beam whose average power is 100 milliwatts, and this beam consists of pulses coming in at 1 hertz. That means each pulse has an energy of 100 millijoules. This isn't the right sensor to use. Let me look for the right sensor. So we include that in our spec, just as a sanity check, as a heads up kind of thing. All right, next item, angle dependence. This one's going to be a little bit more straightforward, I think. Semiconductor response depends obviously on the absorption of the beam. Absorbed light causes an electrical current to flow. It causes separation of charges, and then the electronics causes a current to flow. Okay, whatever. And the current is proportional to the power of the absorbed beam. So first of all, as a general rule, the transmission, reflection, absorption behavior of materials in general is affected by angle. If you remember your basic physical optics. As we approach grazing incidence angle, materials tend to become more reflective. Photodiodes are no exception. So the absorption of light by the detector is to a small degree angle dependent, but much more significant than that. As we saw earlier, our photodiode sensors have attenuating filters added, one built in and a second one removable, to extend the sensor's dynamic range. These filters are usually, not always, but usually absorptive. Usually it's just an ND, attenuating glass filter, NG whatever, depending on the model and so on. And that means that light coming in at an angle is going to be moving through a longer optical path than light coming in at normal or vertical incidence, because it's moving through a longer optical path through an absorptive attenuating filter. It means more of this light is going to get absorbed, which means less of this light is going to reach the detector. So it started off as, X milliwatts, but only maybe 80% of X reaches the detector. So the detector is going to be measuring a wrong value. Okay, so that's something important to keep in mind. The longer optical path increases the absorption more or less as a cosine relation of the incidence angle. I'm going to explain that more or less in a sec. Now, I say more or less because other factors also come into play, such as losses due to reflection off the front surface, which is affected by angle. As we briefly mentioned on the last slide, this image really says it all. Say a picture's worth 1,000 words, which if you think of information theory is actually quite correct. So this image I took out of, if I remember correctly, I took this from one of my favorite optics textbooks from my university days. If I remember right, I think this was from Optics by Hecht and Zajac. Phenomenal textbook. Anyway, so here you can see from our data sheets from I'd say our workhorse model of photodiode power sensor. We call it the PD300, 300 because it measures up to 300 milliwatts, depending on the wavelength, but whatever. So here we see graphs of angle sensitivity, angle dependence for a few different models. We're actually going to be looking at this one with that removable attenuating filter in and out. So if you notice here, at 0, the x-axis is the angle, the y-axis is the relative response. So at 0 degrees incidence, meaning normal vertical incidence, that's 100% response. With the PD300, with the filter in, that removable filter in, it drops down to 87% of what it was at normal incidence. So if the actual power on the beam was 10 milliwatts, if the angle of incidence is 20 degrees, we're going to be reading not 10 milliwatts, we're going to be reading 8.7 milliwatts. Remember, by the way, that if we're talking about a diverging beam, it's not quite as bad because a diverging beam is a solid cone that contains light at all angles up to the maximum outer envelope angle of the cone. So it's something that just needs to be taken into account. Next item, we already mentioned diverging beams, so let's talk a little bit about diverging beams. In some applications, we have a widely diverging beam and we want to measure the total power in the beam. For example, if we're a manufacturer of VCSELs or a systems integrator of instruments, of systems that incorporate a VCSEL. So for fully capturing and measuring a widely diverging beam, a common solution is to use an integrating sphere. The details of that are fascinating, but it's way beyond the scope of what we can really cover in this conversation right now. But basically, all right, here you have an Ophir 6-inch integrating sphere, 4 different ports. So here there's a built-in power sensor, fully calibrated as a system. And then these things generally come with all kinds of accessories. Some of them are automatically included, and then there's a whole bunch of other accessories that are optional depending on the configuration you're going to need to work at and that sort of thing. So here you have a 120-degree acceptance angle port adapter. We have one model of integrating sphere that has a specially designed gold-coated cone that gives the sphere a 170-degree, you heard me right, a 170-degree acceptance angle. And then there's all kinds of fiber adapters and all sorts of different things so you can sample light out to additional instruments like a spectrometer, like a fast photodiode, and then an oscilloscope so you can analyze pulse shape, temporal pulse shape and that kind of thing. Here's my forward button. Okay. In other applications involving widely diverging beams, we might not necessarily really care about the total power. In some applications, we might only care about the power that's incident per unit area on a surface. Think of UV curing or UV, antibacterial treatment of water or surfaces or things like that. Or curing of pigments and that sort of thing. So there, the beam is large and illuminates a surface. It may even be, long UV fluorescent lamps illuminating, a production line surface. And the parameter of interest may very well be the power incident per unit area on the surface, or the total accumulated energy deposited per unit area of surface over X seconds or something like that. So we might be interested in measuring milliwatts per square centimeter or millijoules per square centimeter. So one way you can do it is to use a regular power sensor, and the beam is going to be obviously much bigger than the sensor. You know the area of the sensor's effective aperture. You measure the power, you divide by the area, and you're good. That's often enough how it's done. There are some instruments, we have some at Ophir, and there are others that are designed specifically for measuring irradiance, power density, or dosage, energy density. Here you see one. It's based on a UV enhanced silicon photodiode, but it's calibrated and designed and configured for measuring irradiance and dosage, okay, power density and energy density. You can see, I hope, that there's a diffuser built on the front that provides it provides basically cosine correction to give it a corrected angle response. Saturation. Wait, I'm getting a question here. Is the response of a typical photodiode uniform over the entire active area, different on the edges? Oh, that's an excellent question. In a perfect world, it would be. I have yet to visit a perfect world. So generally speaking, with photodiodes, the only real issue is non-uniformity of the attenuating filter that's built in, and of the second attenuating filter if you have a sensor that uses that. Those are neutral density, ND glass, NG, I don't know, 4, 5, 9, 10, I don't remember. So there is a certain tolerance on the thickness, and therefore on the absorption of these attenuating filters across their area. As far as I know, the silicon photodiode itself doesn't really care where on the photodiode the light arrives, because all of the light is getting absorbed and turned into current. I don't know offhand if that's strictly true. There may be some, but generally speaking, the real source of non-uniformity is going to be tolerance on the thickness of the attenuating filter or filters. And for the Ophir sensors, we actually state that in our data sheets. So yeah, thanks for asking that. I should just mention, with thermal sensors for the higher powers, it's not our topic today, but there's a little bit more of a dependence on getting too close to the edge in many cases, but that's just a side point. Okay, so thanks for raising that. Saturation. So how do we know if we're in saturation? So generally speaking, most laser power meters, have multiple ranges or scales, and if you go above the top of the scale that you're on, it'll tell you over range or something like that. And generally speaking, designers of these instruments design them so that that over warning comes long before saturation. You don't want to set the upper limit at saturation, because as you approach saturation, you generally will start getting into linearity problems. So you don't want to do that. So designers of these instruments always will design the scales so that you're never actually touching on the edges of saturation. But not always, particularly with pulsed beams, as we saw, because with the pulsed beam, you could have instantaneous saturation that has nothing to do with the average power, and therefore has nothing to do with the scale that you're on. The average power, as we saw, may very well be safely within the scale, and yet for that brief instant during the pulse, you're shooting way above it, and you might not even know it. So how do you know if that's happening, since you're probably not going to be getting an over or sat warning in these kind of situations? So there's no clean-cut answer. The only real way to do this is, to a certain extent, to depend on your intuition. So if you sense that something doesn't look quite right, what you do is you then go to a one less sensitive scale and compare. So let's say you're on a 10 milliwatt scale and you're measuring what you're kind of expecting to be 8 milliwatts, and it's telling you 6 milliwatts. I'm just making up numbers. And you're not sure. So what you can do is you go down to the next less sensitive scale. Typically, the scales are divided by orders of magnitude. So let's say after the 10 milliwatt scale, the next scale down in sensitivity is the 100 milliwatt scale. So you switch to that. And now, lo and behold, you do see 8 milliwatts. Now, normally, you're not going to choose the 100 milliwatt scale to measure 8 milliwatts. You'll choose a 10 milliwatt scale, again, assuming that you have one, because you don't want to be too near the bottom of your scale. And obviously, if you've got a 10 milliwatt scale, that would be a better choice for measuring 8 milliwatts. But on the 100 milliwatt scale, you'll still measure the 8 milliwatts. So you can use that as a quick litmus test. If you see that on the 10 milliwatt scale, you kind of were expecting to see 8 and you're seeing 6. You switch to the 100 milliwatt scale and you see 8, that's already a pretty good indication that there may be an issue and it may very likely be saturation. Sometimes you'll hear theories or suggestions or concerns about a beam with a given power, if it's small, causing maybe local saturation on a detector, even if it's not a power level that should be saturating the detector. In a regular single element standard, semiconductor photodiode, that doesn't actually happen. Apparently, we have indications that with very small beams, it might sometimes happen. We haven't actually documented it or measured it, but we have enough indications that we're not poo-pooing the idea. But generally speaking, it doesn't really happen. Obviously, I'm not talking about an imager where one pixel can get saturated, because each pixel is an independent detector element. But here, if we're talking about a power sensor where the whole sensor is one photodiode element, in theory and probably in practice, there isn't really such a thing as localized saturation. Okay, we mentioned beam size. Let's talk a little bit about beam size. This is a question that we get asked very often. How big should my beam be relative to the size of my sensor's aperture? Should I fill the aperture? Should I very much not fill the aperture? So we've got a tension here between two different needs. On the one hand, we want the beam to be big, because if it's focused down small for a given power, we might start to come close to the damage threshold, to power density that might already cause damage. If we're dealing with nanowatts, that's not going to be a concern. But if we're dealing with 100 milliwatts, it focused down small enough, that neutral density absorptive attenuating filter most certainly can get damaged. And you'll see it if that happens. It doesn't take much. So you don't want to be too small. And another advantage of a beam being large is that you're much less affected by small localized non-uniformities, because it gets averaged out. On the other hand, you don't want the beam to be too large either. And why is that? So here we see, I hope the resolution is good enough for you to see the fuzzy Gaussian beam that we're looking at here. Our eyes are very cleverly designed. A very highly talented engineer designed them. And there's a lot of image processing that goes on in our retina, in the optical nerve complex, and then in our brain. So there's edge sharpening and a lot of incredibly brilliant image processing that goes on. So we often will look at a fuzzy beam and we'll see what looks to us like the beam diameter. Typically, we're talking about the 1/e² beam diameter if we're talking about a Gaussian beam. So if we have a beam whose 1/e² beam diameter is shown here, and we put that beam into a sensor whose aperture is just exactly or very slightly larger than that 1/e² beam diameter, to our eyes, it may very well look like the whole beam got in. But actually, if you do the math, we've just chopped off 14% of the power in that beam. That's the math. And we won't even know it. That's an effect called vignetting, which comes, I believe, from the French word for window, which is, I don't remember. I used to know French. I grew up in Canada. So if, on the other hand, we use a sensor aperture that's 1.5 times what our eyes think is the beam diameter, in other words, 1.5 times the 1/e² beam diameter, the math says we're still chopping off something, because a perfect Gaussian never actually reaches zero. Obviously, in this world, that doesn't usually happen. So, but we're going to be chopping off 1.2% of the total power in the beam and not 14%. So in Ophir, in our calibration labs, in our laser rooms, we generally speaking set things up so that the beam will fill somewhere between 1/3 and 2/3 of the sensor's aperture. That's kind of the sweet spot that we like to work at. And last item, spectral issues. Okay, anyone who's at all familiar with semiconductors and optics and where the two of them meet will know that the spectral response of a semiconductor photodiode is not flat. It goes into the quantum mechanical nature of the energy levels of the atoms in the material and the mechanism, the physical mechanism by which photons of light are getting absorbed. I won't go into that, even though I would kind of love to, but I won't go into that. I'll resist the temptation. It's a problem that we geeks have. I'm sorry to say, very often I'm sitting with a kid and something interesting comes up, and I'll say something that I think is really cool, and then I notice my kid's eyes begin to roll, and I realize, oops, sorry, I got geeky on you. Never mind, whatever. It's a problem. It's a problem. Okay, so here we see the spectral response of that PD300, if you remember that typical workhorse model of Ophir photodiode-based power sensor, silicon photodiodes. And here we see two curves. The black line is without that second filter in place, the filter out. And the red line is with that filter in. Okay, so the overall range of the spectral range goes from 350 nanometers with that second filter in already. I think it starts only at 400 nanometers and goes out to just the beginnings of the near IR. 1100 nanometers I think is pretty typical. So it's not very wide, and it's certainly not flat. Some parts of it are more flat than others. Okay, now let's compare that to the spectral distribution of the light being emitted by a typical LED. Okay, I tried to place it in scale and in the correct relative position. So this is a blue LED, or a UV, more like a blue LED. Typical spectral bandwidth here is going to be, somewhere like 10 or 20 nanometers, full width, half maximum. So it's going to be over here. Obviously, you've got, red LEDs, which are going to have a similar spectral shape, but they'll be placed more like over here rather than over here. Same idea. If you want to use a photodiode to measure I'm not going to talk about broadband light sources like white light, that's out of the question, but wideband, not quite monochromatic like a laser. All right. So there are some issues, and this is a very, very common measurement need nowadays, as LEDs are becoming more powerful and higher quality, and more of their parameters can be controlled, and the price still kept reasonable. If you're going to use a photodiode to measure a wideband source, then there's a few things to be careful of. Wait, I jumped ahead of myself. Sorry about that. So first of all, the fact that my spectrum is wide means that there's light of more than one wavelength. Now, because these photodiodes are not spectrally flat, we calibrate them with a full spectral curve. So if the light and then each wavelength gets its own calibration factor stored on board the detector, and the meter reads that at the same time as it receives the analog signal and combines everything and gives a readout of the power. But if the light actually contains a whole bunch of different wavelengths, each wavelength should have received a different calibration factor. So I'm introducing an error to a certain extent by having a wider spectrum as opposed to the nice narrow spectrum of a laser or a laser diode. So if I'm in the part of the spectrum where the spectral response of my sensor is quite flat, then the error that I'm introducing by having a wideband source is probably going to be not very significant. On the other hand, if I'm talking about a red LED, let's say, and in this part of the sensor's spectral response, the slope of the curve is really, really steep, then that even small widening of the spectral content of the beam could introduce a huge error into my reading. So you need to be aware of this. There are photodiode-based sensors that are specifically designed for this. They have a filter, a coating placed on them that flattens their spectral response. We have such a detector in the Ophir family of photodiode sensors, and there are others. There are various tricks that can be used to deal with this kind of an issue, but the main thing is to be aware of the issue. One of those tricks is what you see here. What happens if we're talking about not a slightly wider than comfortable spectrum, but a spectrum that's located in a completely different part of the spectrum? Let's just go back for a second. In other words, not here and not here, but here, or okay, I don't have room on my screen to go, but all the way off to the right. So what do we do then? Let's say, we're talking about terahertz, or we're talking about, mid IR measurements, but at powers that are too low for a thermal sensor that usually has a much broader, flatter spectral response. So usually what we use there is something called a radiometer. Sometimes we'll use a photodiode, but using what I like to call exotic semiconductors. So for far IR, thermal imaging applications, we have MCT, mercury cadmium telluride, we have PBS, and others tend to be somewhat expensive. It may or may not be a good solution. Very often we use a radiometer, and a radiometer, it's a word that kind of is used in many different ways by many different people. In this kind of application, we're talking about a detector that has a spectrally broad response. So we've just addressed one of our issues, and it overcomes the lower sensitivity that such detectors normally have, for which reason we would have wanted a photodiode, by using an optical chopper to modulate the beam, which means we're not going to be using a thermal sensor. We're usually in these kind of solutions, we're going to use a pyroelectric detector. I'm not going to get into the details. If you're familiar with that, you'll appreciate it. We'll use an optical chopper to modulate the beam at some well-known, well-controlled frequency. And then we're going to use a digitally synthesized lock-in amplifier to ignore any signal that's not at exactly that modulation frequency. And what we've just done with that, I know in the Ophir instruments that are based on a radiometer, the background is cut down by something like 3 orders of magnitude, and the noise is cut down more or less completely. There's noise and there's offset, there's background. So the background is cut out more or less completely. Sorry, the noise is cut down by about 3 orders of magnitude. Sorry, switch those two around. And that enables us to work way below what would have normally been the noise floor of that kind of detector. And we use that for measuring in those areas where we're outside the spectral range of photodiodes, silicon, germanium, and InGaAs. So, we're either below UV or beyond 1.82 microns, something like that, and power too low for broadband thermal sensors. So these kind of areas are where we're going to use the radiometer as a very elegant solution. Okay, so in summary, we did a very, very brief overview of the basics. And then we looked at a bunch of different issues and the challenges and tricks that they present. The challenges that they present and the tricks that are often used. Sometimes I gave you a few tricks that are specifically Ophir tricks, but I also shared some, solutions that are, that are out there for all these different issues. Pulsed beams, and we talked about VCSELs as a good example of a challenging pulsed beam to measure. We talked about angle dependence and how we deal with that. But for example, by providing cosine corrected angle response, or an appropriate type of a sensor. Diverging beams, either capturing the entire beam and measuring its total power, usually using an integrating sphere. I'll just mention that at Ophir, for example, we have one model of integrating sphere that's a multifunction sphere. It has built in a calibrated integrated power sensor, but it also has a built-in fast photodiode with a BNC output to a scope, so you can also analyze the temporal pulse shape, and another port, fiber, for a fiber adapter, so that you can sample a little bit of the light out to a spectrometer. We actually designed that specifically for VCSEL-related measurements. And other applications we mentioned where we're not interested in the total power, just in the irradiance or in the dosage. And we looked at an example of an Ophir solution for that. The idea is pretty straightforward. Talked about saturation. Sometimes momentary saturation can not give itself away. If you have a reason to suspect that, we gave the tip of maybe, comparing the reading at 2 different power scales and seeing if there's a difference. That would be a dead giveaway. Talked about beam size issues and spectral issues. Okay, I had said 50 to 52 minutes. We're at 54 minutes. Okay, I hope the 2 minutes are for a good cause. Okay, so that's basically what I wanted to give over. I realize that's like a ton of information packed into not a ton of time. I hope this was helpful, dare I say maybe even interesting. If you have any questions you still want to ask online, you got a couple more seconds in which to do so. Otherwise, I'm going to leave this slide up, as I said, for a couple of minutes. If you want to take down my details and contact me afterwards. My name again is Mark Slutsky. I'm the product manager for power and energy measurement solutions here at Ophir Photonics. This is my email address, mark.slutsky@mksinst. That's short for mksinstruments.com. You could also use ophiropt.com. That still works. Or you can contact us through our representatives or the Ophir office in your various countries, or through our website. I hope this was helpful again. Thank you very much for being with us. Stay healthy. Have a very nice rest of the day.